Hey everyone, today we are going to solve the LeetCode question median of two sorted arrays. Okay, first of all, let's talk about the definition of the median. The median is the middle value when a sorted array is split exactly in half. If the number of elements is odd, the median is middle element. So for example, 1, 5, 8, so median is 5. If it's even, the median is average of two middle elements. So in this case, 1, 3, 5, 8. So we use 3 and 5. And 3 plus 5 is 8. And divide 2. So that is 4. So median is 4 in the second case. The first idea that may comes to mind is to merge the two arrays and extract the middle value. So for example, merge two sorted array and get length and check if total length is even or odd. If even, return the average of two middle elements. If odd, return the middle element. So this is easy, right? This code does calculate the median, but this approach has time complexity of order of m plus n log m plus n, because we use sort, so which does not meet order of log m plus n requirement. So to achieve order of log m plus n, as many people may already know, we need to use binary search. The key point to the problem is partition and comparison. The key to solving this problem efficiently is to divide each array into left and right parts appropriately. So left part means smaller number group, and the right part means larger number groups. Okay, I guess next question is why divide into left and right? As I told you, the median is a middle value when a sorted array is split exactly in half. If total number of elements is odd, it's a 1 in the center. If even, it's the average of two center values. So we can compute median by finding the maximum of the left half, or the average of max of the left and the minimum of the right. But it's not always the case that all elements of nums1 are smaller than those of nums2, or vice versa. So for example, nums1 equal 1 and 2, and nums2 equal 3 and 4. So you can simply append nums2 after nums1 to get like 1, 2, 3, 4, which is sorted. And in this case, median is 2 plus 3 divide 2. That is 2.5. So how about this case? Nums1 is 1, 3, 8, and nums2 is 7, 9, 10, 11. If we try to merge the array directly and sort them, we will get 1, 3, 7, 8, 9, 10, 11, where the value 7 from nums2 is smaller than 8 from nums1. This means that we cannot simply merge two arrays. So we divide each array into left and right parts. The left part of nums1 and nums2 forms smaller group, and the right part forms larger group. We calculate partition in such a way that entire combined array would be sorted. Since actual merging and sorting the array would take more than order of log m plus n time, so we simulate the sorted array using calculation instead. Okay, this is an image of algorithm, but actually these partitions are not correct. But please look at them just to get the idea of how algorithm works. So left max 1 is right before partition. So partition is here. So right before number is 3, right? So max left is 1 is 3. And the minimum right 1 is right after partition. So that is 8, right? And max left 2 is right before partition. So that means 7, right? And the minimum right 2 is right after partition. So that is 9. And if max left 1 is less than or equal to minimum right 2, so in this case, max left 1 is 3 and minimum right is 9. And the maximum left 2 is less than or equal to minimum right 1. So max left 2 is 7 and minimum right 1 is 8. So we compare this group versus this group and this group versus this group. So if we meet this condition, we can say array is correctly partitioned. That's because so left part is 1, 3 and from nums 1 and 7 from nums 2, right? So if we create a left part, so we can create like 1, 3, 7, right? And how about the right side? So right side from nums 1 is 8 and 9, 10, 11 from nums 2. So if we sort them, we can create 8, 9, 10, 11. And this is a left part, this is a right part. If we combine two arrays, so we can create 1, 3, 7, 8, 9, 10, 11. So whole array is sorted, right? So we try to this kind of position of partitions. And one more thing, you don't need to compare the left and the right within the same array, like max left 1 and minimum right 1, because both arrays are sorted individually based on what the question said. Okay, let's talk about how to determine partition. The partition that determines left and right side is calculated using binary search, left and right. And look at this. The partition 1 is the number of elements on the left side of nums 1. Partition 2 is the number of elements on the left side of nums 2. And the length 1 is the length of nums 1, and the length 2 is the length of nums 2. And look at the partition 1. So left plus right divide 2. I think you are familiar with this formula, right? When you solve the question with binary search. And how about the partition 2? Left, the length 1 plus length 2 plus 1, and the divide 2 minus partition 1. So regarding the partition 2, since both partition 1 and the partition 2 represent the total number of elements on the left side, they should sum up to the half the length of merged nums 1 and the nums 2. This gives the next formula like this. So partition 1 plus partition 2 equal length 1 plus length 2 plus 1 and divide 2. To calculate partition 2, we move partition 1 to the right side. So that should be partition 2 equal length 1 plus length 2 plus 1 and divide 2 minus partition 1, right? And I think somebody wondering why plus 1. So when total number of element is even, the median is average of two central value, right? This means you can add left max value and right minimum value, then divide by 2. When total number of element is odd, the median is single central value. By adding the central value to the left max value, the logic becomes consistent for both even and odd cases. I mean, simplify the logic. Okay, from now on, let's see how it works. So nums 1 is 1, 3, 8, and nums 2 is 7, 9, 10, 11. So initialization, so length 1 is 3, right? And the length 2 is 4. And the left pointer is 0, and the right pointer is 3. So I mean length 1. So we use nums 1 for binary search. And partition 1, so part means partition. So partition 1 is left plus right divide 2. So that is 1, right? And partition 2 is this formula, length 1 plus length 2 plus 1, and I think this is 8, and the divide 2 is 4. And the partition 1 is 1, so 4 minus 1 is 3, right? So in this case, so partition 1 is 1. So do you remember? 1 is a number for left side. So we have one number for left side. So that means here is a partition, and we have only one number, right? And how about a partition 2, 3? So we have 3 numbers on the left side. So 1, 2, 3, and the partition is here. So in this case, max left 1 is 1, right? And the minimum right 1 is 3. And the max left 2 is 10, and the minimum right 2 is 11. And check if we have correct partition with this formula. But we don't meet this condition, so that is false. So that means we can't create sorted array because this is a virtual. So left part is 1, 7, 9, 10, right? So left part is 1, 7, 9, 10. And the right part is 3, 8, 11. So if we combine these two arrays, that should be 1, 7, 9, 10, 3, 8, 11. Oops. So this is not sorted, right? That's why we will execute binary search again. But before that, we should narrow the search range. So since these two input array is sorted, so we don't have to compare like max left 1 and minimum right 1, because it's obvious minimum right 1 is greater than or equal to maximum left 1, right? And maximum left 2 is definitely less than or equal to minimum right 1 and minimum right 2. So that's why we compare cross array like max left 1 is greater than minimum right 2. So if the condition is true, it means that the partition of nums1 has moved too far to the right. In other words, we need to search for the smaller numbers, so we move right pointer to like right equal partition 1 minus 1. In the opposite case, we move left pointer to left equal partition 1 plus 1. For current case, so max left is 1 is greater than minimum right, that is 11. So this is a false, right? So that's why we move left pointer to partition 1 plus 1. So partition 1 is 1 plus 1, so that is 2. So next time, our left pointer is index 2. Okay, let's talk about the second binary search. So now left pointer is 2, so coming from this formula, and the right pointer is still 3. So let's calculate partition 1 and partition 2. And I forgot to add formula, but do you remember partition 1 is left plus right divide 2. So 2 plus 3 divide 2, and 5 divide 2 is 2, right? And partition 2 is length 1 plus length 2 plus 1. So that is 8. Divide 2, and that is 4, minus partition 1. 4 minus 2 is 2, right? So look at this image. So we have two numbers on the left side of partition. So that's why partition is here, and we have two numbers on the left side. And partition 2 is also 2. So that means we have two numbers on the left side. So 7 and 9, right? Looks good. So in this case, max left 1 is 3. And the minimum right 1 is 8. And the max left 2 is 9. And the minimum right 2 is 10. And check if we put partitions correctly with this formula. But it's false, because 1, 3, 7, 9 plus 8, 10, 11 is not sorted, right? So that's why let's narrow the search range again for binary search. And the formula is same, this one. So max left 1 is greater than minimum right 2. So in this case, max left 1 is 3, and the minimum right 2 is 10. So it's false, right? So that's why we move left pointer to partition 1 plus 1. So partition 1 is 2. So 2 plus 1 is 3. So next time, so left pointer should be index 3. Okay, let's talk about the third binary search. So now left pointer is 3 and the right pointer is 3. So partition 1 is 3. 3 plus 3 divided 2. And the partition 2 is, so this is always 8, right? Divide 2 and 4 and minus 3, and that is 1. And look at this image. So we have 3 numbers on the left, and 1, 3, 8. And we have 1 number on the left, 7, right? So in this case, max left 1 is 8, and minimum right 1 is infinity. So actually there is no number on the right side. So let me explain later. And max left 2 is 7, and minimum right 2 is 9. And regarding the infinity, so we've already seen twice. So some of you may already understand, but algorithm checks this condition, right? In this case, there is no number remaining on the right side of nums 1. So this means the key comparison is max left 1 is less than or equal to minimum right 2. So max left 2 is less than or equal minimum right 1. So we want to ensure it doesn't cause the false result. So we make it always true. To do that, we set minimum right 1 to infinity, which is greater than any number. Since it's right side of partition, we use infinity. When we reach the far left of the partition, that means index 0, we use negative infinity. We need like a smallest number. Okay, so now let's return to the main point. So max left 1 is 8, is greater than equal to minimum right 2, 9. Looks good. And max left 2 is 7. And we want to make this part always true. So that's why we use infinity. And this is true, right? So both sides are true. So that's why we will get true from this if statement. That means we found a valid partition that results in sorted array. So in this case, left side is 1, 3, 7, 8, and the right part is 9, 10, 11. So we can create these two arrays. So if we merge them, we will get 1, 3, 7, 8, 9, 10, 11. So it's sorted, right? We've finally found the correct partition point where the merged array would be sorted. The last point to cover is what we mentioned at the beginning. So do you remember? The median is a middle value when a sorted is split exactly in half. If the total number of elements is odd, it's a middle element. If it's even, it's the average of two central elements. So in this case, nums1 has length of 3, and nums2 has length of 4, making total odd number. So we just return the single middle value. And then when we finish the third binary search, the partition is like this. And do you remember why we add +1 here? In the case of odd total number, we include the central value in the left half. So the median is the maximum of the two left sides. So max left 1 or max left 2. So in the end, we compare these two numbers, 8 versus 7, and definitely 8 is greater than 7, right? So that's why in this case, we should return 8. And for just in case, let me put even case. I think you can easily understand now. Yeah, so that is the basic idea to solve this question. So let's jump into the code. Okay, let's write the code. First of all, if length of nums1 is greater than length of nums2, in the case we swap two arrays, so return self dot call same function again, and nums1 should be nums2, and nums2 should be nums1. So since one of arrays can be significantly longer than the others, we always perform binary search on the shorter array. It's efficient, right? And then length 1 and length 2 equal length of nums1 and length of nums2. And left and right equal left is start from index 0, and the right is length 1. And let's execute binary search. While left is less than or equal right, we continue. So partition 1 equal left plus right divide 2, and partition 2 equal length 1 plus length 2 plus 1 divide 2 minus partition 1. And then max left equal, so float, so this is a minus infinity if partition 1 equal 0. Else, if not the case, nums1 and partition 1 minus 1. And minimum left, not left, right 1, and actually max left 1 here. And this is a minimum right 1 equal float, and this is an infinity because the right side. And if partition 1 equal length 1, else nums1 partition 1. And then max left 2 equal float, and this is the left side, so negative infinity. Oops, if this is a partition 2 equal 0, else nums2 and partition 2 minus 1, and minimum right 2 equal float and infinity if partition 2 equal length 2, else nums2 and partition 2. And then if max left 1 is less than or equal minimum right 2, and max left 2 is less than or equal minimum right 1. And then in the case we can sort whole array, so that's why check length is even or odd. So if length 1 plus length 2 and percent divide 2, so we use remainder equal 0. So that means this is an even case. So max of left side, so max left 1 versus max left 2 plus minimum right 1 versus minimum right 2, and divide 2. Else, this is a odd case, return max of max left 1 versus max left 2. If not the case, else if max left 1 is greater than minimum right 2. So do you remember? In this case, we should move right pointer to partition 1 minus 1. So right equal partition 1 minus 1. Else left equal partition 1 plus 1. I think that's it. So let me submit it. Yeah, looks good. And the time complexity of this solution should be order of log m or order of log n, because we use shorter array for binary search array. So that's why. And the space complexity is, I think, O1. We don't use an extra data structure. Yeah, so that's all I have for you today. Please support me with the actions such as comment and hitting like button. I'll see you in the next question.